Unit 6A is about air pressure and wind. Now, when you hear a weather report, you sometimes might hear the person say that there's a low pressure system coming in, or we have high pressure in the area, and most people don't pay attention to that. But it turns out this is a really indicative signal of what the weather is doing and what it's going to be like in the next few days. Here are the Unit 6A learning outcomes, so go ahead and pause the video and write them down in your notes. We're going to start with the idea of atmospheric pressure. We were all born on the surface of the earth under a certain amount of pressure, so we don't really notice it because we've been in it all our lives. But there is a pressure being exerted on all of our heads from the air above. And this little cartoon is showing you how this column of air is pushing down because it's gravitationally being pulled by the earth onto the surface of the earth. Now we know that there's more air, more gas molecules closer to Earth, so it turns out the force of this air gets less and less as you go higher and higher in elevation. The average air pressure on Earth is known as the sea level pressure. And I'm showing you a scale here with pressure listed in a couple different units. Pressure is a weight, right? You push on something, that's a pressure. It's a force. And so one unit of force is PSI, or pounds per square inch. And this might ring a bell because we pump our tires, our bike tires, and our car tires to a certain number of PSI, maybe 30, 35 PSI for your car tire. Well, the air pressure at Earth's surface is about 14.7 PSI. The units here, though, are not in PSI because we don't really use that in science. We use either millibars, which are metric, or inches of mercury, which were devised a long time ago, and they're still used, but not as much. So what I have here on this scale is average sea level pressure. It turns out that on average, the sea level pressure is 1,013.25 millibars. Now, if you think about the metric system and millimeters and meters, in units of pressure, a millibar is part of a bar. In fact, there are 1,000 millibars in a bar of pressure. So you might be thinking, well, if the pressure is near 1,000, why don't we just say it's 1 bar? And it is close to 1 bar. But the thing is, average sea level pressure listed in bars would be 1.01325. And that's just a lot of annoying decimal points. So we use millibars instead to stick with mostly whole numbers. Inches of mercury is another unit that I'll talk about in the next slide. I'd like you to pay attention to the numbers here in terms of a strong high pressure and a strong low pressure system. We go up to about 1,040 millibars for very strong high pressure regions and down to about 980 millibars for low. So this right here is the normal range of pressure on Earth. The extremes that are high are areas that are cold, where dry, dense air is pushing down. Areas that are extreme in the low end tend to be hurricanes, because hurricanes are extreme low pressure events. And I'll get to that in just a minute. But let's look at this mercury barometer. It was invented in 1643 by an Italian inventor named Torricelli. He used a dish filled with liquid mercury. Now today we know mercury is rather toxic and this wouldn't really be a good idea, but he didn't know that. Then he put a tube into the mercury that he evacuated all the air out of. And the air pressure that pushed on the mercury, it pushes down on the cup, that forces mercury up the tube. And then he would measure the height of that tube above the level of the mercury, and that would be his reading for air pressure. Now, if air pressure increases, so let's say the air is pushing down harder, what's going to happen to that mercury level? Well, it's going to rise, right? If you push harder here, it's going to force this to rise. And it's going to be higher pressure. If, on the other hand, the air pressure lessens and it becomes less of a force on that dish of mercury, then the mercury is going to fall. And so sometimes you might hear the mercury is falling, and that means that low pressure is coming into an area. So that's a mercury barometer. An aneroid barometer measures without liquid. That's what aneroid means. And it uses this expanding and contracting chamber that's hooked up to an arrow that can show you on this dial which way the pressure is going. So millibars are listed on the inside, inches of mercury are listed on the outside. And what's amazing about air pressure is looking at these words here. Air pressure dictates whether or not storms are coming or the weather's going to be dry. So if the air pressure starts to drop from 1020 to 1010 to 1000, then we're looking at a change. Going down to 900 or 980, then we're expecting rain. And if we go even lower, we're expecting stormy. So falling pressure means rain or storms are coming. On the other hand, if the pressure goes up, then we're going to have dry, fair conditions. And fair doesn't necessarily mean warm. Fair means dry. So there's a lot that atmospheric pressure can tell us about the weather. Some of these lowest barometric pressures ever recorded were related to hurricanes. And as I said, hurricanes are intense low-pressure systems. The lowest pressure ever recorded in the United States was Hurricane Wilma with a value of 882 millibars. And in the world, there was a typhoon in Japan that reached down to 870 millibars. And hurricanes in the Pacific Ocean are called typhoons. So it's the same phenomenon as a hurricane. So 882 and 870, let's look back at that previous instrument. This goes down as far as 940. So those atmospheric pressures were so low, they wouldn't have even been recorded on a normal barometer. Let's move on to wind. Wind is simply the movement of air from high pressure regions to low pressure regions. For example, here's my amazing drawing of a tire. And you pump up your tire to air pressures that are greater than the pressure outside, right? So you have high pressure in the tire compared to outside. Now, if you get a hole in the tire, wind that's created, the movement of air is going to go from high pressure to low pressure, right? You wouldn't expect a hole in the tire and then air to go rushing in. So maybe this is one way to remember that wind always moves from high to low pressure. So we have two basic types of measurements that we use with wind, and that's the wind direction and the wind speed. The wind speed can be figured out by something called a cup anemometer that spins and then records how fast it's spinning. The direction of wind can be figured out by something called a weather vane that lines up with the direction of the wind motion. What's really important here is that winds are labeled for the direction from which they blow, not towards which they blow. So for example, this girl has an umbrella that's blowing to the left, and we're going to say this is east and this is west. So she is being blown by an east wind. It's coming from the east. So here's a weather map showing what's called ISOBARS. Bars, again, are pressure, so ISO means same pressure. Unlike the ones we looked at a while ago called isotherms that are temperature. And what you can see here is we have H for high pressure, L for low pressure. Around each of these we have contours of air pressure in millibars labeled every 4 millibars. As you would expect from what I just told you, air should move from high to low pressure as this green arrow shows. However, there are other factors that affect the wind. I want to show you these little things called station models that are here. These indicate ratings from a particular city, and the city is right where the circle is. And then the symbol that's coming off of that city is showing the speed of the wind. So if you have a line with just 2 feathers, I call them, then you're between 21 and 25 miles per hour. If you have one with a darkened triangle and a short line, then you're looking at 61 to 66 miles per hour. The other thing is that the wind direction is indicated by the direction that the little flag is moving, or the station model. So up here, we have a wind coming from the north. This is a north wind that's hitting the station. Don't think of it as a flag flying in the wind, otherwise you'd think that this has wind coming from the south. Over here, we have wind coming from the east. Over here, we have wind coming from the west. So in general, winds are sort of blowing away from the high and towards the low, but they're not directly doing that, and I'm going to explain why in just a second. Another thing about this symbol here is it's related to station models that we're going to learn about in Lab 7. This page is going to be something that you're going to want to keep with you, especially during exams, and it's got a lot of different kinds of information of station models, models of weather data at a particular place. So here we have the wind speed, again, the symbols, and then miles per hour or knots per hour if you prefer. We're going to be putting these on weather maps in Lab 7. So the 3 factors that affect wind include something called the pressure gradient force. that is simply what I just showed you, that air moves from high to low pressure. Here's 1016 millibar pressure, here's 992 millibar pressure, and so air is going to move from high to low, from left to right. The other thing to notice is the distance between each of these isobars. Remember, they're representing every 4 millibars. The closer together the lines are, the stronger the winds, because the faster the pressure change. If they're farther apart from each other, then we're going to have weaker winds. So if you notice here, we've got isobars close together here, and symbols that are indicating very fast winds, symbols that are over here. Out in this area where the isobars are farther apart, the winds are not as fast. The second thing that affects a wind is the Coriolis effect, and this is the result of Earth rotating on an axis. In the northern hemisphere, winds are deflected to the right, and in the southern hemisphere, they're deflected to the left. Let me show you this example. If our Earth were not rotating and we sent a rocket from the North Pole down to 90-degree longitude on the equator and set it to go straight, well, then that's what would happen. But because our Earth rotates, instead, our target is going to be missed because the Earth rotates under us, and we seem to be deflected to the right. And you can see that here as well. Now this is all upside down compared to the southern hemisphere where things are deflected to the left, but let's stick with the northern hemisphere. So the Coriolis effect deflects winds to the right. Finally, friction with the ground also affects winds by slowing it down. And I'm showing you something that I actually just got out of the internet today. Today is Tuesday, October 6th, and there's a hurricane called Hurricane Delta out here in the Gulf of Mexico. These are the projections over the next few days, and the colors indicate speed. So red is a major hurricane with 111 mile per hour winds or faster. Then we have, as it hits land, slowing down to a hurricane level, and in gray to a tropical depression. And that is strictly because the hurricane, the winds are hitting land. So all of these factors together, the red arrow shows the wind that's going from high to low pressure. The Coriolis effect moves it to the right, so the arrow looks like this. And then the friction drags it backwards, so in the end, the net direction is this giant arrow here. Coming up next, lots of videos.